Hello everyone and welcome to the presentation of the work The Magnon Mean Scattering Time of YIG derived from Seebeck effect experiment. My name is Vittorio Basso and I'm presenting this work with co-authors Alessandro Sola, Patrizia Salone and Michaela Korfelling, and this work has been performed in the Istituto Nazionale di Ricerca Metrologica in Torino, Italy. So the topic of this work is to study the Seebeck effect. So let's see a few slides to know what this effect is. So one of the most common systems that is studied is a bilayer, one with a ferromagnet, an insulating ferromagnet, for example the yttrium iron garnet, and a metal, platinum for example, with a large spin-Hall effect. So in the Seebeck effect one applies temperature gradient upon YIG, and then measure voltage, transverse voltage difference on platinum. This under a certain applied field. And this is the geometry shown in the picture. Well, how can we interpret the effects? If we put a heat current into YIG, then we can expect that his heat current is not only carried by phonons, but also by magnons. So this magnon diffusing into the YIG at a certain point enter also into the platinum layer. And in the platinum layer they create a magnetic moment current or a spin current. And thanks to the inverse spin-Hall effect, this magnetic moment current is transformed into an electric current or an electric voltage in an open circuit. Why do we have this effect in a ferromagnet? Well, essentially because at non-zero temperature we have thermal excitations, and these thermal excitations are also spin waves or thermal spin waves. Thermal spin waves have a property, they have a certain velocity, they can diffuse from one side to the other. Therefore, if we put a temperature gradient and we look at the hot part, we will have a lot of magnons, a lot of thermal magnons, and this number of magnons will be less in the cold side. Therefore, they will diffuse, exactly like hot particle diffuses in a gas. As a result, the magnetization distribution, as a function of the thickness, is not the equilibrium one. It will be different. This non-equilibrium effect is what is driving the injection of a magnetic moment current into the metal. So if we go into the metal, we observe a certain current which is injected there, a current of magnetic moment. But because of the inverse spin-Hall effects, this current is partially deviating in a lateral direction. Theta SH is the spin-Hall angle, so it's a property of certain heavy metals. This angle is positive for tantalum and tungsten and negative for platinum. So here we are using the angle for the magnetic moment, not for the spin, so it's in opposite with respect to the normal literature. And therefore we can reveal the presence of a magnetic moment current by measuring an electric current or an electric voltage. In the case we have shown before, we have a positive heat current. That means a negative magnetic moment current and a negative spin-Hall coefficient for platinum. Therefore, the resulting electric current is positive. Well, this is the interpretation, but how material behaves in terms of the Seebeck effect? Well, in the literature, in the past years, there have been extensive measurements of these effects, and in particular here we are interested to the temperature dependence. So in the slide you see the results on the YIG platinum bilayers done by two different groups. So there is a certain phenomenology which is quite well confirmed. Let's take the picture at the left and let's look first at the red points. These are for the bulk material, so 1 millimeter thickness can be considered bulk for YIG. And what do we observe? What's the main feature? The fact that Seebeck coefficient, the ratio between the voltage and temperature gradient becomes larger when we decrease the temperature up to a certain point, around 80-90 K, and then it decreases down. So there is quite nice and well-defined peak. This phenomenology is pretty much changed if we change the thickness of the YIG. As you can see, the presence of the peak is almost completely, the peak almost completely disappears for small thicknesses. So this is quite interesting to speculate about the properties and the nature of this diffusion and motion of magnons in ferromagnets. One question is, what is the reason for the peak? This is a question that has been raised before, and we have already answers. So in the literature, you will find explanations of this low temperature peak of the spin-Seebeck effect in terms of interaction between phonons and magnons. So the idea put out by Adachi et al. Was that as the thermal conductivity in insulator very often has a peak in that temperature range, then they suppose that there should be an interaction between the phonons that are responsible for the peak and the magnons. So the heat current also pushes the magnons in terms thanks to an interaction between them. We are not too much convinced of this explanation, so we try something different. And what we have tried is to study the interaction of the magnons with the possible scattering sources. And what are the scattering sources if we have magnon diffusing? Well, we have to consider defects inside the material. We have to consider the finite boundaries, the boundaries of the sample if we have a finite samples, and we have to consider also other magnons. A mechanism that when we go to high temperature should be important. What is the method that we have used? Well, first of all, let's say something about the magnetic moment current. Magnetic moment current is different from the electric current. It is a non-conserved current. So the most important property of magnetic moment current is the diffusion length, the length over which this magnetic moment current disappears. If we look at the theory, we see that this diffusion length is due to two facts. One is the magnon lifetime, the other is the magnon scattering. Magnon lifetime can be related to some known parameter of ferromagnet, alpha, the damping. So the larger the damping, the smaller is the magnon lifetime. It's quite a reasonable assumption. The magnon scattering can be studied like any scattering of particles. So we can relate the magnon conductivity, if you like, to a typical collision time. That's the focus of our work. We want to compute, to understand something of the typical collision time for these magnons. And how to do this? Well, we have a lot of data available. So can we compute the mean collision time from the data? Well, to do that, we need a theory. The theory for diffusion. So I can only show you the result here, but just to say that at the left-hand side of the equal sign, we have the spin-Seebeck coefficient. We want to use experimental data for spin-Seebeck coefficient at the left. At the right-hand side, we have a lot of parameters, but most of these parameters are known. The spin-Hall angle of platinum is known. Thermomagnetic power coefficient for a ferromagnet is known. Then we have thicknesses, spin diffusion lengths of several materials, well, platinum and YIG. So we can compute the missing one, but essentially the missing one is the magnetic moment conductivity of YIG, or if you want, the mean collision time of YIG. So what we have done? We have taken this equation, we have taken the data for the bulk, and we have computed the typical collision time for YIG. And now I want to show you the result. So this is the time constant for collision plotted as a function of temperature. The data, the points, are the Kikuchi data for the bulk. So as you can see, there are two typical behaviors as a function of temperature. Low temperature as a function of temperature. A low temperature one that goes as 1 over square root of temperature, and the high temperature one that goes as 1 over T to the 4th. And these two behaviors are exactly what are expected for magnon defect collision, the low temperature one, and magnon-magnon collision, the high temperature one. So as you see, the behavior in the log scale is quite good. So we describe very well the peak just by having two mechanisms that compete. So at high temperature, the magnon-magnon is the most relevant one. Therefore, the mean magnon collision time that describe a peak like the one of the bulk Higgs is just a sum of two things. If we compute the mean free path, which is due to the interaction with defect, we find a number which is 10 microns, quite huge number. If you remember, we have seen that experiments for thin films included thicknesses exactly around and below that thicknesses. Therefore, what happens? If we want to take the full set of data and we want to describe this by adapting the theory of the bulk that we have just done, what we have to do? We have to include another source for scattering, that is the interaction with the boundary, so the finite thickness of the sample. If we do that, we introduce another scattering mechanism, which is the binary one. But now what we can do, we can take the data for the bulk, adapt for finite thicknesses, adding the scattering of the boundaries, and then describe the full set of data. And this is the main result. So the black curve and the black points are the bulk. So here we have just translated the peak into these two mechanisms, magnon-magnons, magnon defects. In order to describe the lower thicknesses, we have introduced the scattering interfaces. So while the black one is just a description of the data in a certain sense, the rest is a fit without any free parameter, because we have just introduced a scattering which is proportional to the thicknesses. The result is quite nice, I would say, because in one shot you describe the whole phenomenology. So let me summarize and conclude. So our work was aimed to describe the spin-Seebeck effect, and in particular the temperature dependence. So I think we have shown you that you can describe the peak of the temperature dependence of spin-Seebeck effect by just having two mechanisms, the interaction with defects of the magnons and the interaction with other magnons. It seems that the interaction with phonons, so something much more detailed and complicated, is a second order effect that is not important, at least to describe the main features of the peak. What is also very nice is that we can get in one shot also the whole phenomenology as a function of thickness. The phenomenology is captured very well, at least in its general features, and we have just used the data of the bulk and introduced a source of scattering for the interface. You can find all the details in the paper mentioned below. And with this, I thank you very much for your attention, and bye-bye.